So comparing now this, so you find this manganese 4 plus, okay, the green one, the energy shift to higher, the rising edge region energy shift to higher in comparing to the manganese 3 plus, and also the pre-edge intensity, because you have more unoccupied state, so your pre-edge intensity is also higher than the manganese 3. Okay, and now let's go to another example. This we are talking about coordination number and the local geometry effect. Let's look at these 3 figures, A, B, and C. At figure A, you see this the solid. We have 2. One is solid line, one is dashed line, and there's 2. One is for nickel, and if there's bounded to 4. The nearest neighbor is 4 nitrogen, and for dash line, the nearest neighbor is 4 sulfur atoms. And this means the nickel has 4 coordination number, and for the case B, nickel has 6 coordination number, and C is also 4 coordination number. In figure A, you can find once the nickel is bounded to 4 nitrogen or 4 sulfur atom, although they have same coordination number, but the spectrum is different. Okay, and if you bound it to 6 coordination number, even the atoms type is the same as figure A, but the spectrum is still different. Okay, if you consider all nickel bounded for 4 nitrogen case, if the geometry is in a tetrahedral, or it becomes a square planar. Here the D4H space group is a square planar. You can find the spectrum is quite different. For the TD, there's a tetrahedral geometry. The spectrum is this solid line. You have very strong pre-edge peak here. For the square planar, it becomes this dashed line, a very weak intensity pre-edge. So from the pre-edge intensity, you can also distinguish the local geometry symmetry. It's a tetrahedral or square planar. Okay. So for the advantage of X-ray absorption fine structure, what can we have? It's a direct structural determination for any form of material, any isotope, any spin state. It can direct determination of oxidation state. We already mentioned this. And the disadvantage of X-ray absorption fine structure is it's box spectroscopy. So that means it's an average structure. And you have little angular information. Most of the information comes from the atom-to-atom distance. And it only gives out local structure information because it's a short-range ordering. Okay, so another is a limited sensitivity. And you require the synchrotron X-ray source. But the experimental setup is quite easier. You have synchrotron source come in, and this is entrance slit, and you have a monochromator. This is a double crystal, and use a 2D sin theta over lambda because this D spacing is fixed. So you changing the instant beam, the angle, then you can tune your instant photon. And once the instant beam come into your experimental hatch, and you can have an ion chamber to measure the instant beam intensity. Here is your sample, and you can measure the transmission beam intensity. Well, this measurement under transmission mode. If you want to measure in fluorescence mode, you can tune the sample in this direction, and you put detector at here. Okay. Now, let's look at this picture. Here is your X-ray absorption spectrum. And if you consider in microscope, you have instant beam intensity I0, and you measure after a certain thickness of your sample or concentration, you obtain the intensity Ix. And according to Beer's law, you can have the absorption coefficient like this, equal to the natural log Ix over I0. And if you consider it's two atoms, one is absorbing atom X, the other is the neighboring atom Y. There's a distance D. And your instant photon with H nu knock out one s electron, it can go up to an occupied state. And here is your near edge feature or pre-edge feature. And once it can go out to, you keep increasing your instant photon energy, can excite the electron to a continuum state. Once it to the continuum state, it can be a free electron. You can consider it a wave. And here your outgoing wave will backscattering due to the neighboring atom. And so you have an instant outgoing wave and a backscattering wave. And the interference between outgoing and the backscattering wave will give out a modulation feature of your accept region. If you consider such kind of interaction for the accept region, you can consider here is the absorbing atom. Here, this is the neighboring atom. You excite one electron, knock out, and this electron interaction with the neighboring one, this one, and the backscattering to the absorbing atom. And this path is true, and we consider such kind of a process as a single scattering. And most of accept region, you can only use a single scattering can already interpret the accept spectrum. And for the near edge spectrum, the energy is less than the accept region. So the wavelength should be longer. And you can consider like this. You have absorbing atom and electron knock out to this atom here, and go to this atom and back to the absorbing atom. So now you have path 1, 2, 3. And this such kind, you path 1, 2, 3 can have also like this, 1, 2, 3. And you can have path 4, 1, 2, 3, 4. And we name this multiple scattering. And for when we want to interpret the X-ray absorption near edge spectrum, we have to include a multiple scattering. Okay, now we already mentioned the basic theory of fundamental phenomena of X-ray absorption spectrum. And now we go to talking about the data analysis. I think to understand the background of X-ray absorption spectrum is not very difficult for you. But most of people have difficult on the data analysis. And here is your experimental data. The dashed line is you subtract the background, and you do you transfer to get such kind of, we call it accept chi function, and you do Fourier transform. Then you can do the fitting. So in general, you have experimental raw data. Then you remove the background, remove abnormal data, and then you do a background subtraction and the normalization. Then you do a Fourier transform. Then you can fit in the K space, or you can fit in the R space. And for the fitting, we are based on this formula. I will go to this one. We call this an accept chi function. Actually, this chi function is defined by you have a absorption coefficient and minus your mu 0 and divided by normalized by your h jump mu 0 at k equal to 0. And here mu k is defined like this. It's square root of 2m e minus E0. E0 is the H energy. and over your H bar. And in this equation, here Nj is a coordination number, and Fj is a backscattering amplitude from each of the Nj atoms in the shear at the distance Rj. And with the Debye-Waller factor, this term here. And here sigma square is relative mean square displacement in R space. And S0 is the amplitude reduction factor. And in this equation, you have the sign function. And in the sign function, you have a phase shift, delta J. This delta J is the total phase shift, and the lambda K is the photoelectron mean free path here. So the formula is like this. And so when you have experimental data, and you just follow according to this, you have mu E, and then you can obtain the chi function. And this chi function, you can times the K cubic vector, and you enlarge the information. You will scale the information. For example, in these figures, and the horizontal is a K, and the vertical is the axis accepts chi function times the K cubic. For such kind of oscillation, accept chi function, the amplitude, this amplitude is related to the coordination number, and the scatter, and the scatter will be related to the phase and the shape, and the other is bond length. And here you see the frequency, the oscillation frequency we are related to the bond length. And the information content of accepts in general for the accuracy it's about 0.02 angstrom for the bond length, but for precision it could up to 0.005. And for the coordination number, the error is plus minus 1. And the ligand type, that means atom type can be plus minus 10. And the maxima, you can probe the distance about 4 angstrom. Because you can see from here, this one. Actually, this copper case is a superconductor, bismuth 2212. And near the copper, you have 5 oxygen. It's a square pyramid. 4 oxygen in planar and 1 oxygen in apical. And this first shear is copper oxygen distance. The red line is fitting result. You can find the distance. The black line is your experimental result. And up for 4.5 electron, the intensity become very weak. So the accepts actually is a short range. So that's why we say here, well, you can obtain information just near the absorbing atom around 4 angstrom. And now let's look at this parameter. If I have structure here, this the central absorbing atom is nickel, and here you have nitrogen. Okay, I see. Okay, this sulfur atom, and this nitrogen. And so, if you calculate the backscattering amplitude, and you can find this here. We calculate the case. You have 4 atoms are all in nitrogen. Okay, if this backscattering is from the sulfur, or backscattering from nitrogen, or if I replace this from 1 sulfur change to selenium, and we can see the backscattering amplitude will become like this. So here the black line is the backscattering contribution from the selenium.